Welcome back to the Math Professors. If you like content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover linear correlations. So really linear regression. And we're going to use a particular method called the linear correlation coefficient, R method. And R really measures the strength of our linear correlation. And we're going to use a table to determine the Pearson value, which is going to be our critical value, and then we're going to compare that to R. So I have two situations here. Data that looks linear like this, and data that doesn't look linear like this. Now what I mean by linear is it looks like these points are kind of trending around this line, as opposed to over here, these points almost look like raindrops on a field. Now here's kind of an example of what would happen is we can compute R, and we usually use our calculator to do that, but we do have a formula to be able to compute R. And then we're going to look at the critical value, which can be found using, a table I'm going to display. Now, in this case, we can see that R is bigger than the critical value, verifying that we have a linear correlation. Now, sometimes R is a positive number, sometimes R is a negative number, so we don't really look at the sign of R, we actually look at the absolute value of R, because really the critical value is both plus or minus this number, and to be past the threshold, you need to be bigger in absolute value than whatever a critical value is. So really, I just look at both positive numbers, and if this number is bigger than this number, I know that it reaches that threshold, therefore it's linear. And in this case, I can see that R is not quite big enough to meet this threshold, so I know that this is not going to have a linear correlation. It's going to look more like raindrops. So we have two different ways that we can predict. Now, if we have pattern to our dots, I know if I pick a number here, it's going to be, pretty close to this orange line. As opposed to if I pick a number over here, I don't know where it's going to be. It's probably going to be somewhere between, the minimum and the maximum. So when we try to find a predictor equation, we can kind of see why we use both of them. So in this case, we know that it's going to be close to that line. So this is a linear equation that has some y-intercept and it has some slope. So some y-intercept and some slope, and then we can just plug in our x value. So x is here. If I plug it into this orange thing, it's going to spit out this, right here on that line, which is going to be pretty close to the data. Or if I plug it in over here, it's still going to spit out the orange line, which would be really close to the data. So really, this linear regression line kind of acts as the center or the middle of your data. Now, this data doesn't have as much pattern, so how would you do the middle of the data? Well, all I know is it's going to live between the minimum and the maximums, and really our best predictor would just be, I'm trying to predict, what the y value is if I'm given the x value. So since this is sporadic, my best y value is just averaging up these y values, because at least I know this is going to minimize the particular error I might predict. So if it's linear, you use a line with slope. If it's nonlinear, you use a horizontal line. With that horizontal line, y is just going to equal this constant, which is just the average of the y values. So let's get to an example. So given the data, drive time versus wellness / how happy you are with your drive, I'm given this data, I want to answer these particular questions. So first, I can see all the commute times with their associated wellness. I want to know if there exists a linear correlation. Now, I really want to know if there's like a linear pattern to this data. When I plot this x comma y, does that actually, look like a line, either going uphill or going downhill? We won't know yet. So in order to do that, what I need to do is I need to compute R. Now, in order to compute R, I'm going to plug this data into the calculator. So over here, we're going to go ahead and hit stats. And then it's already highlighted on edit. So go ahead and hit edit and then just basically hit enter. So stats enter. Now you're going to see an L1 and L2. L1, we're going to plug in this data. And then L2, we're going to plug in this data. So first line being L1, which will be the first column. L2 will be that second column. All right. Now once we're done with that, we have to hit stats, and then we have to go over to test. So click over to the right twice, and you can either press up or press down a bunch, but we're looking for linear regression t-test. And go ahead and hit enter. Now there you'll see some information, but what we're looking for is we're looking for R, so you're going to have to slide that down until we can find R. And what we can see is R is equal to negative 0.989. I'm going to round to 3 sig figs. Now again, we don't really care that it's negative. We only care about the absolute value of r. And we're going to compare it to table A6, which is right here. And what I know is that I have, as far as data points, I have 1, 2, 3, 4, 5, 6, 7 pairs of data. So when I go over to 7, I'm going to use alpha, or an error of 5%. I can see that it needs to exceed 0.754. 1, 2, 3, 4, 5, 6, 7. So the critical value, or the Pearson value, is equal to 0.754. Now we can answer, does a linear correlation exist? Well, is this number bigger in absolute value than, say, this number? And we can see that it is. This number is bigger in absolute value than this one. So yes, a linear correlation exists. So yes. All right, now I want to determine the predictor equation. Well, remember in the beginning, we had 2 different predictor equations. Sometimes we'd use the regression line, which was y hat. Sometimes we'd use the average of the y's, which is y bar. Now, since this is linear, what we know is y hat is going to be equal to a plus bx. We're going to use, that predictor. Let's do that back in orange the way we had that before. So this y hat is equal to a plus bx. Now, we have the values of a and b. Now, if we go back to our calculator, when we went to linear regression t-test, if we tab this down, we can actually see there is an a and a b. So we get y hat is equal to, I'm going to use a couple decimal places. So a is 87.26, and then plus b, well, b is negative. Actually, we can see that b is going to be negative because this was a negative correlation, which means the dots are going to be running downhill. So the one thing you can say is that the sign of r is actually going to match the same sign as your slope. So b being 1.096, so 1.10 times x. All right, so now that I have my predictor equation, what I want to know is what is the slope and what is the y-intercept of this thing. So I know that the slope is, the coefficient in front of x, so, our slope is going to be negative 1.10, and then the y-intercept is going to be, I'll write it as a point. So we know that x is equal to 0, and then y is going to be equal to 87.26. Okay, so now what I want to do is I want to be able to graph this regression line. So we can do that on our calculator as well. And in order to do that, we need to build ourselves, a window that would be useful. So I can see that for the x values, this is the L1, which is the commute time. I go from 5 all the way to 68. So maybe let's go up to 70. So 1, 2, 3, 4, 5, 6, 7. So this will be, 10, say 20, 40, 60, and then 70. And I know that the wellnesses looks like they go from like 0 to like 100. So I'm going to go up to maybe 90. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if I want to plot this data, what I know is it needs to be 5, 80.1. Let's put some numbers on here. So 20, 40, 60, 80. So I know this is going to be 5, 81, which is going to be about right there. This is 10, so 5's halfway. That's our first point. Next is going to be 12, 72, so about right here. Then I have 30, 59, which is about right here. 37, 51. I am doing my best because how tight this is. And then we got 40, 39, so about right there. 53, 26, so about right here. And then we have finally 68 to 12.5, which is going to be about right here. Now maybe I should have put these dots in blue like I had before in the previous, look at this. So that is our that's our lineup. We can see that it looks like it does have pattern. Actually, what's interesting is this is supposed to predict this line, and if I was to graph this, what you'd actually get is y hat is going to essentially go through that data. So that's going to be y hat, which is equal to 87.26 minus 1.10 times x. Now I'm going to show you how to do this on the calculator as well. So on the calculator, you already have your data in there into L1 and L2. So what you're going to want to do now is you're going to want to press window, and then you want to do the same window. Maybe go from 0 to 70 for your x values, and let's go a click mark of 10. You can see where I did that to scale. And then for the y values, we're going to go from 0 up to 90, and it looks like I also use the click of 10, so we'll do a scale of 10. So now when you press y equals, delete any equation that you have there, and then you'll see plot 1, 2, and 3. Press up and then turn on that first plot. You'll see it highlighted. And then when you hit enter, you're going to see these data points. Now the line's not in there because I didn't plug it in yet. So let's do that. Let's press y equals, and then let's type this equation into that first line, and go ahead and hit enter, and then you're going to see that line scoot right across that data. Okay, so now that we can plot this by hand or plot this on a calculator, let's ask if we can make predictions, because that's the whole idea of regression lines, is can I make a prediction given data? So let's make predictions. So what is the wellness of a person who drives 20 minutes? And then we'll also do 2 hours after that. So if I want to do 20 minutes, what I know is that y hat is going to be equal to, remember this is the predictor, it's going to be 87.26 minus 1.10 multiplied by 20. Remember, what I'm really asking for is, what's that at 20? So if I pop it into this line, I should be able to get, whatever that prediction is. So if we do that at 20, so let's try that, plugging those numbers in, I get 65.26, which actually is about landing where I expect it to be. So this is 65.26. Now the last question, it says, what about 2 hours? Now remember, 2 hours is going to be 120 minutes. So this is kind of an important one I wanted to talk about. And if I go 87.26 minus 1.10 times 120, well, what would actually happen here? Well, what I get is I get a wellness of negative 44.74. And notice that wellness likely would stop at 0. So what this is this last one, I'd consider this as error or extrapolation error. Let's say it that way. Let's say error, let's say slash, from extrapolation. When you extrapolate, what you're trying to do is you're trying to predict data far past the given values. And what I know is the farthest I can really go is about 68 or 70. So when I'm trying to predict way over here at like 120, this is far past the given data. I can only guarantee this is linear around these dots here, around my data. I don't know what's going to happen beyond that. So be careful trying to extrapolate too far, because it's going to be full of error. So the last bit of data I want to do, and I'm not going to make a big example out of it, I just want to show you a nonlinear example. So what I have is I have ACT scores versus SAT scores for 1, 2, 3, 4, 5, 6, 7, 8 students. And I want to say, note that this is not linear, and the way we do that is, again, on our calculator, you're going to plug this into L1, this into L2, and then you can go to test, linear regression t-test, and then you can find your R value. So what we have for R is equal to 0.543. Now, the linear correlation coefficient using alpha is equal to 0.05. I'd get a critical value for 8. Remember, there's 8, so it's going to be a different number. Over here, you're going to see that this is 0.707. So the reason why this is not linear is because the absolute value of R doesn't, exceed the value of this critical value of this Pearson coefficient. So we can really get an idea if we try to graph this exactly what it looks like. Now, I'm going to graph it by hand. I'm also going to probably show you a graph over here. So we know that we have to go, we're going to go from, let's do this graph that are dots. And I'm not going to do the scale. The scale's already over there. But when we look at this graph, we actually see these points look a lot more like something like this. Now we might say it possibly has, I don't know if it really has any trend, but you can kind of see it looks more like that raindrops we showed. Do an appropriate axis. What I chose to go from, and I'm not going to be super specific, window, I went from, 130 all the way up to 230, and then I went by tens. And then over here I went from 1850 all the way up to 2400. Because remember, I have to do all these data values have to fit in here, and all L2 has to fit in here. And then when we graph it, we can see that this really doesn't look linear. So our best prediction for this type of data is going to have to be the horizontal line, which is going to be, y hat. So what is y hat? Well, y hat's going to basically be the average of these values. It's going to be right here. This is going to be y hat, which is going to be the sum of y's over n. So stats, we can, you have a couple ways to calculate this, but if you add up all the y values and divide by 1, 2, 3, 4, 5, 6, 7, 8, you're going to get this is equal to 2152.5. So if you're asking any predictor values, like what would the prediction value be at, say, 150? Well, it wouldn't matter. You're going to plop it up to this line, pop it back out, you're going to get this number. What about at 160? You're still going to get this number. What about at 220? You're still going to get this number. So if the data doesn't have any linear pattern, what you do is you just use the same value for every single prediction. So if you like the content, please subscribe.